Welcome to the lecture on hydroboration. Hydroboration is part of Unit 3. Unit 3 is on addition and elimination reactions. This hydroboration is an addition reaction. It is an electrophilic addition. Hydroboration. In hydroboration, diborane B2H6, which is the dimer of borane BH3, adds to the double bond of an alkene to form a product called organoborane. As I said, diborane is made of two monomer units of borane and it is a dimer of borane. And these two monomer units BH3, 2BH3 are bound together in an unusual type of bond that I am going to explain later. So the boron of BH bond in borane is the electrophilic portion of this reagent. The boron is the electrophilic part of borane. Therefore, this boron adds to the less substituted carbon, the carbon that would be less stable as carbocation, and hydrogen adds to another carbon atom which is more substituted in the alkene. This is the structure of diborane. Actually, two monoborane units are connected here. This is part of one monomer, borane with two BH bonds. The third BH bond is here. The two electrons of this BH bond are spreaded between boron, hydrogen and another boron. So the two electrons of this BH bond are moving towards the vacant orbital of this boron. Therefore, two electrons are spreaded between three atoms and this is called a three-centered bond. Similarly, here is another borane with two BH bonds here. The third bond is here. This third bond has two electrons and these two electrons are spreading from here to the vacant orbital of the adjacent borane. So every boron in borane has a vacant orbital. To that vacant orbital, these electrons are moving. Therefore, two electrons of this bond are spreaded between these two boranes and a hydrogen, and this is also a three-centered bond. And these two three-centered bonds are looking like a banana in shape. Therefore, these two are called banana bonds. This is one banana bond and this is another banana bond. This diborane is usually dissolved in an ether like tetrahydrofuran and it is very reactive with alkenes. So when diborane is dissolved in DHF, it dissociates into monomer units and the monomer is forming a complex with THF. This is the tetrahydrofuran part. The lone pair of electrons are of oxygen are making a covalent bond with boron, and this is the complex species obtained when monoborane combines with THF. When an alkene is added into this complex, this borane is released from oxygen and the borane starts reacting with alkene. Hydroboration is an electrophilic addition where hydrogen and BH2 of a borane are added to the double bond of an alkene or to the pi bond of an alkene, resulting in the formation of alkyl borane. This reaction involves concerted mechanism, a single step mechanism where hydrogen and BH2 are added from the same side of the double bond, and in the reaction goes through a cyclic transition state. So during this reaction, the pi bond of the double bond in alkene and the BH bond in borane are broken and two new sigma bonds are made, and all these processes are taking place simultaneously, leading to the formation of cyclic transition state. So hydrogen and boron are added from the same side of the double bond. Therefore, it is called syn addition, and the reaction goes through a cyclic transition state, a four-centered transition state. Finally, the pi bond and BH bond are broken and these two new sigma bonds are generated. So hydrogen and boron were added from the same side. Here, boron is the electrophile. Boron in borane has only 6 electrons in its valence shell, and the 6 electrons are present in the 3 BH bonds, and therefore boron has a vacant orbital and it is 2 electrons short of an octet. Since it is electron deficient, it is an electrophile. According to Markovnikov's rule, electrophile is always added to the less substituted carbon. Therefore, boron is electrophile and it is added to the less substituted carbon of an unsymmetrical alkene, and the hydrogen goes to another carbon which is more substituted. As I said, boron of borane is connected to 3 hydrogens through single bonds. Therefore, it has only 6 electrons in its valence shell. These 6 electrons are the electrons present in the 3 BH bonds. And then the boron, as I said, has a vacant orbital and it is 2 electrons short of an octet. Therefore, it is an electrophile. So boron of borane is electrophilic in nature, and then boron has 3 BH bonds. Therefore, every BH bond is capable of reacting with an alkene. Therefore, in hydroboration reaction, all 3 BH bonds of borane are reactive and they react with 3 molecules of alkenes or alkynes, resulting in the formation of trialkyl borane. Here I have taken an example of an unsymmetrical alkene, propene. This side we have CH2 and this side we have CH connected to a methyl. So this is more substituted part of alkene and this is less substituted carbon of alkene. It reacts with diborane in ether. So diborane in ether dissociates to monoboranes. So this monoborane reacts with the double bond of alkene. Boron, the electrophile, joins with the less substituted carbon. Hydrogen is added. It is released from borane as hydride, a nucleophile. That H minus joins with the hydride nucleophile joins with more substituted carbon. As I said, it is not completely removed as hydride. So the double bonded, the pi electrons are gradually moving towards boron and the BH bonded electrons are gradually moving towards more substituted carbon. So we have a cyclic transition state. Finally, boron is added to less substituted, hydrogen is added to more substituted carbon atoms. As I said earlier, in boron we have three BH bonds. So one BH bond has reacted with one alkene. There are two more BH bonds. Another BH bond reacts with another alkene, resulting in dialkyl boron. Still there is one more bond here, BH bond, that reacts with one more alkene, resulting with in trialkyl boron. So in the first step, an alkene reacts with boron to form monoalkyl boron. This step takes place at a faster rate as a bigger alkyl group has joined with boron. There is some steric effect operating here, and because of that the second step is little slower. And not only that, as an alkyl group, an electron donating group is added to boron. It is donating electrons to boron and makes it less electrophilic. Therefore, it reacts slower at a slower rate with another alkene. So once a dialkyl boron is generated, so two alkyl groups are there, both are electron donating, they donate electron to boron, therefore the electrophilicity of boron becomes less. Therefore, it reacts with another alkene at a very slower rate, resulting in the formation of a bulky trialkyl boron molecule. 9-BBN is a reagent used for hydroboration in a selective manner. 9-BBN is an acronym of 9-bora bicyclo-331-nonane. This is 9-BBN. It is a bicyclic molecule. This boron-carbon is the bridge. This side we have 3 carbon atoms that I have mentioned as 3 here. In another side we have 3 carbon atoms, that is the next 3, and there is only one atom in the bridge, that is 1. Therefore this molecule is called the bicyclic structure has 9 atoms and the boron is in the 9th place. Therefore it is called 9-bora bicyclo-nonane, 9-BBN. The reaction of 1,5-cyclooctadiene, if you start numbering from here, 1, 2, 3, 4, 5. In carbon number 1 and 5, we have double bonds. Therefore, this molecule is 1,5-cyclooctadiene. With this, when we add boron, diboron in ether, the boron diboron splits into monomer units, and one boron monomer reacts with this double bond. When it reacts with this double bond, boron is added to one carbon, hydrogen is added to another carbon. Both carbon atoms are in similar environment, therefore hydrogen and boron can be added to any one of the 2 carbon atoms. And after this hydroboration, another BH bond reacts with another alkene. Now the reaction is selective to make a 6-membered ring on both the sides. This side we have a 6-membered ring and this side we have 6-membered ring. So the next boration is taking place in a selective manner so that we get 6-membered rings on both the sides. 6-membered rings are usually stable. Therefore, the reaction takes place in this way. And this is the same as this structure. And this is 9-BBN and this is the actual structure of the molecule. And very often when we write the 9bbn in reactions, and it's difficult to write the bigger structure in every equation, so that it is written as BH bond here with two rings. So bicyclo, that is represented like this. So wherever we use 9bbn in reaction mechanisms, so we use this symbol to represent 9bbn. A di-substituted borane with two bulky alkyl substituents is bigger in size. It reacts only with the terminal double bond of a molecule with multiple number of double bonds and triple bonds. So in borane, in 9bbn, borane has only one BH bond. The other two BH bonds are replaced by alkyl groups, the bigger groups. So because of its bigger size, it cannot approach the internal multiple bonds, the internal double bonds or triple bonds. It can approach only the terminal double bond of the molecule with multiple double and triple bonds. So with this molecule, when we add 9bbn in ether, the pH bond reacts only with the terminal double bond and not with the other double bonds or triple bonds. Therefore, 9bbn is very selective in its hydroboration. So any di-substituted dialkyl borane is very selective in its reaction, and it reacts only with the terminal double bond and not with the internal double or triple bonds. So when an unsymmetrical alkene is treated with borane in ether, it undergoes alkylation to give monoalkyl borane, reacts with still it has two more BH bonds. It reacts with two more alkene units, resulting in the formation of trialkyl borane. So when any unsymmetrical alkene is added to borane in ether, three molecules of alkenes are reacting with borane, resulting in trialkyl borane. This is called hydroboration. And we are not going to stop the reaction here. We are going to oxidize this organoborane with alkaline hydrogen. Trialkyl boranes are oxidized with alkaline hydrogen peroxide. So with hydrogen peroxide, we add sodium or potassium hydroxide to generate a peroxide anion. This peroxide anion is nucleophile and it attacks the electrophilic boron of trialkyl borane. So this nucleophile, this minus, interacts with the vacant orbital of borane and it makes a sigma bond here. So once a sigma bond is made here, boron gets a negative charge. Boron, due to its smaller size and it has only 5 protons in its nucleus, therefore it cannot accommodate more number of electrons. So once it gets negative charge, immediately it tries to become neutral. Therefore it pushes out an alkyl group from here as R minus. The R minus that comes out from here attacks this oxygen, making a new bond, pushing this hydroxide out. And this is how one oxygen has been inserted between boron and alkyl group. In between boron and alkyl group, an oxygen has been inserted. One oxygen has been inserted between boron and carbon of the alkyl group. Now another peroxide anion again attacks in the similar way here and inserting one more oxygen between another boron carbon bond. One more hydrogen peroxide anion is reacting again with the resulting product and it is inserting one more oxygen. So the reaction of every peroxide ion is inserting an oxygen between boron and carbon of the alkyl group. Therefore, finally we get trialkoxyborane. And this trialkoxyborane is reacting with the hydroxide anion that is expelled in every reaction. So the hydroxide attacks boron, forming a minus charge on boron. And in order to become neutral, the boron oxygen bond here is broken and alkoxide anion goes out. So one nucleophile attacks, another nucleophile RO minus goes out. It takes up your proton from water and becomes an alcohol. Similarly, another hydroxide ion attacks boron, pushing out another alkoxide. One more hydroxide attacks here, pushing out another alkoxide. All the alkoxide ions which are coming out take up your proton from water molecules and they become alcohols. So all the three alkoxy groups in trialkoxyborane are removed from boron and we are ending up with boric acid, trihydroxyborane or boric acid. Along with that we get three molecules of alcohols. So this R is the alkyl group. So when the alkene is propene, alkyl group is N-propyl. So this R is N-propyl and the alcohol will be N-propyl alcohol. So with the unsymmetrical alkene, boron was added to the less substituted carbon and to the same carbon OH is added. Therefore, with an unsymmetrical alkene, hydrogen is added to more substituted, OH is added to less substituted carbon in the hydroboration followed by oxidation reaction. And this is one way to prepare a product which looks like anti-Markovnikov's product. When we do hydration in an unsymmetrical alkene, the hydrogen as H plus was added to less substituted carbon and water OH group was added as water to the more substituted carbon. And here we find hydrogen is added to more substituted, OH is added to less substituted. It is contrary to Markovnikov's rule, but it is not following a reaction path which is against Markovnikov's rule. The reaction is perfectly following Markovnikov's rule. The product looks like anti-Markovnikov's product. Thank you.